So here we are discussing linear combination of vectors. We've already seen about collinearity under the umbrella of linear combination of vectors. Let's actually look at this term called coplanarity now. You already know what coplanarity means. If I have vectors in the same plane, it's called coplanar. But now we have to see how linear combination of these vectors can let me know whether vectors are coplanar or not. For that, let's look at these three important points. Let's look at the first point. It says three coplanar vectors are always linearly dependent. I want you to notice the difference here as far as collinearity was concerned. So collinearity was you had two vectors. So two vectors were collinear if they were linearly dependent. So there it was, two vectors were collinear if they were linearly dependent. Here it is, three vectors. Three coplanar vectors are always linearly dependent. So it's very similar. The property there and the property here is very similar, just that we were dealing with two vectors there, and here we are dealing with three coplanar vectors, right? And in both the cases, if they had to be collinear, they had to be linearly dependent, and here also if these three coplanar vectors have to be linearly dependent. So if I say that, okay, I have three vectors A, B and C in the same plane, right? If they are coplanar, if they are in the same plane, that would mean they are linearly dependent. What does that mean? That means if I take a scalar xa bar plus yb bar plus zc bar is equal to 0, if I take a linear combination and I equate it to 0, multiplying them with scalars, not all x, y, z need to be 0. Well, of course, if they are 0, then obviously the result will be 0. But I can still make this expression 0 even without making all three of them 0, right? So there can be a non-zero xyz combination that can make this 0. So these three have to be linearly dependent if they are to be in the same plane. Likewise, if three vectors are non-coplanar, so three non-coplanar vectors are always linearly independent, right? So if what I do is if I take this c bar and if I make sure that it somehow points like this, it points outside the vector, so the vector outside the plane, so the plane is here and it points outside the plane at an angle theta, then in that case, if I take the linear combination, what will happen? Can somebody say? What will happen is, this combination can be 0 only when x equal to y equal to z equal to 0. For no other combination of x, y, z, this expression can be 0. If a, b and c are not in the same plane, right? That means they have to be linearly independent. So this was one more point, and I want you to know this difference. It's very similar to the collinearity properties, but there we were dealing with two vectors and here we are dealing with three vectors, right? That's all the difference that you need to remember between the two. So coming to the third point, this is not very relevant to coplanarity actually, but nevertheless this point was slightly important, so I had to bring it. More than three vectors are always linearly dependent. So if I have somewhat like four vectors, and if I take their linear combination, then this combination, these vectors will always be linearly dependent. That means I can make this expression 0. I can make this expression 0 even with non-zero x, y, z, w. Which means, fine, one of them can be 0, two can be 0, but not all will be 0, right? Not all will be 0. So obviously if all of them are 0, the expression will be 0. But I can even have a non-zero combination, something like a 1, 2, 0, 0 or a 1, 0, 2, 0, something like that. I can have a non-zero set of combination of x, y, z, w which can make this expression 0. That is when I'll call them linearly dependent, right? So what you have to understand is, if you have more than three vectors, then they are linearly dependent. There's one more property that I wanted to mention, so let me make some space for that and let's look at that property. Now coming to this last point as far as coplanarity is concerned, this point is about coplanarity of points. Until now what we were looking was coplanarity of vectors. Just the way if you recall collinearity, we first discussed, the first 2 points were about collinearity of vectors, and then the last point that we saw was about collinearity of 3 points. What we will do here is, we have already seen the coplanarity of vectors. Now we will see collinearity of 4 points. So we'll see coplanarity of 4 points. In collinearity, what we saw was collinearity of 3 points. Here we will see coplanarity of 4 points. This property that we will see is valid for 4 points. Let's look at this property. So as you can see here, all these 4 points seem to lie in the same plane, right? But how do we ensure? How do we check algebraically by the help of vector algebra to see if these 4 points are in the same plane or not? That is what we are studying this topic for, right? That is what we are studying linear combination of vectors for. So I'm not proving this property again, just like the way I did for collinearity of vectors. You can always prove it using section formula, but since it's not very required to understand why this property is true right now, let's just look into what the property is and accept it under the same lines as collinearity, right? The property is very similar, just that instead of 3 points we will be discussing about 4 points now, and the rest of the property is exactly the same, right? So this property says that these 4 points that you see here, A, B, C, D. So A bar, in the bracket if I put A bar, what does that mean? This actually means that I'm referring to the position vector of A bar. So if I have my origin here somewhere, the vector which goes from the origin to this A bar, so it's going to this point, A bar, is your small a bar. The one which is going from the origin to B is small b bar, right? The one which is going from the origin to C is small c bar, and the one which is going from the origin to D is your small d bar. So this is what I mean by small a bar, small b bar, small c bar, small d bar, right? So you have 4 points, you have their position vectors. Now these 4 points are coplanar if there exist scalars x, y, z, w, such that this first condition holds good. And there's one more thing to be mentioned here. Not all x, y, z, w are 0. What does that mean? I'm taking the linear combination of these vectors. What are these vectors? They are position vectors. So I'm taking a linear combination of these 4 position vectors, these 4 pink position vectors that you see. I'm taking a linear combination of them. And what does this statement mean? This linear combination is 0 with not all of them being 0 at the same time. That means there is a non-zero x, y, z, w combination possible, right? Fine, one of them might be 0, 2 of them might be 0, but not all of them can be 0, right? Once again the same statement that I've been repeating again and again, all of them can be 0, right? But that's not what decides whether they are linearly dependent or not. What decides whether they are linearly dependent or not is something like, can you have a 2, 3, 0, 0, like your x being this, your y being this, z being this, w being this? Can you have a 2, 3, 0, 0, something like a 2, 3, 0, 0, where you have at least one of them non-zero and still make this expression 0? That is when you can call them linearly dependent, right? That's what I've been trying to explain. So here, if there is any such combination possible where with a non-zero, at least a non-zero x, y, z, w, at least one of them being non-zero, the combination can still be 0, right? Then that makes sure that the first condition is taken care of. And what does this indirectly mean? This indirectly means that a bar, b bar, c bar, d bar are linearly dependent, right? That is what this condition means. And anyways, we have seen in the previous property that, okay, 4 vectors, more than 3 vectors are always linearly dependent. So this first condition has to be taken care of. The second and the more important condition is these scalars must sum up to 0. The scalars that you are using for your linear combination and equating it to 0, these scalars must actually sum up to 0, right? This is very similar to the collinearity property that we saw, right? There you had x plus y plus z equal to 0 as your second point. Here you have x plus y plus z plus w equal to 0, right? Because you have 4 vectors here to be that you're dealing with, right? 4 points and their position vectors that you're dealing with. There you had 3 vectors. So this is all that you needed to know as far as coplanarity of 4 points is concerned. This condition, this particular property can take care that your 4 points are coplanar. If any of these two are violated, then you will have something like this. One of these points will not lie on the plane. They might just end up lying somewhere here. So you might have your C bar somewhere, you might have your C somewhere here, and your position vector of C bar going like this, right? So that can be out of the plane if especially the second condition is violated, right? So with this we complete collinearity under the umbrella of linear combination of vectors. Let's look at a few miscellaneous points which will be useful from the exam point of view and from the concept point of view also. So a few miscellaneous points, a few techniques of how to check collinearity. This is one technique, but using determinants also you can check whether three vectors will be collinear or not. Let's look at a few miscellaneous points. That's why I'll put them under the heading miscellaneous, and they can be useful at times. So let's proceed with the miscellaneous points.